Or if you're ever wondering what are contra and co vectors, and isn't it enough to just know what vectors are that we also have to worry about these additional terminology? Or worry not. We're going to try and develop some intuition behind what a contra vector is and what a co vector is. And we're going to see that it's actually a very interesting and useful concept, which will help you in your studies, especially if you were to look at text on fluids and general relativity or even special relativity for that matter. So let's dive right into it. Now, one of the intuitive ways of understanding these two sort of different species of vectors um, is to just look at the position vector, but and look at a very simple transformation of coordinates. So let's try and do that. So I'm going to write this as contra versus co-vectors. So let's say I have my xy coordinate system, and I'm going to measure positions in units. Let's say the only ruler or a scale that we have is has a basic unit of 1 meters. All right, so that's a unit of measurement. So we're going to draw these vertical lines. So I'm going to start with 0. This one is at 1 meter. This is at 2 meters. So let's say this is meters. And likewise for the y-axis. So this is 1, this is 2, this is 3, perhaps this is 3. And let's say I'm going to locate the point which is at 2, comma 2. I'm going to draw a position vector there, this. And so this is the point 2, comma 2. In vector notation, we can write this as that the position vector r is, maybe I'll start with writing xi plus yj, which is 2i plus 2j. Now notice this I and j are unit vectors along the x and y directions. The only unit vector we have at our disposal is a vector which is measured in units of 1 meters. Right? So this is a unit vector. That's the 1 meter unit vector. So that's I, and this vector is j. All right, so that's good. Now let's say someone were to give you a ruler which can measure distances in units of centimeters. So we're going to redraw our coordinate system, but this time we're going to perform measurements in centimeters. So we have this in centimeter and this in centimeter, which means that for every 1 meter length we have in the old coordinate system, we'll have 100 dashes in this manner. And each of these now constitutes a new unit vector, which we call I prime, which is 1 centimeter along the new, rather this will be x prime and this will be y prime. So it's 1 centimeter along the x prime direction. Right? So what we've done here is then going from this coordinate system to this coordinate system is we've just rescaled our axis. We've just rescaled our coordinate axis. And now we're going to measure distances in units of centimeters. So if I were to go back and locate the same point again, right, which was at 2 meters, comma 2 meters in the original coordinate system, we know that the position vector of the point will remain where it is. We haven't done anything except that the units of measurements have changed. Since 1 meter is equal to 100 centimeters, the new units, the new location of the, or rather the new units in which we label our coordinates would be 200 centimeters, comma 200 centimeters. So I can write this in terms of the new coordinate system that we have defined and the new unit vectors we have defined in the following form. We can say r, the same position vector r, is now 200, but this time the units that we're using to measure is I prime, because I prime sort of is trying to capture the fact that our ruler is now has a spacing of 1 centimeter. That's the minimum spacing of a ruler that we have is 1 centimeter. So I can write the same position vector as 200 I prime plus 200 j prime. Now notice how I prime and the original unit vector I are related to each other. So I prime is actually the old unit vector I divided by 100. Similarly, j prime is the old unit vector along the y direction, j divided by 100. But once we've divided the unit vectors by 100, we see that the corresponding components of the new vector, which we can call x prime and y prime, have been scaled up by 100. In other words, I can write the same position vector r as, let's say, instead of using 100, I generalize this and I say that the new position vector is obtained from the old position vector by scaling down the old position vector by units of, say, s. And likewise, we'll use symmetric scaling for now, that the new j prime is obtained from j by scaling down by s. Then we find that the new x prime, so if I were to write this as x prime I prime and y prime j prime, then this new x prime is nothing but scaled up. The component, the new component along the x direction is the old component x scaled up by the same amount s, right, I prime, plus this y component is also scaled up by s j prime. But notice that I prime is just I divided by s and j prime is j divided by s. So I can also rewrite this as I by s plus sy j by s. The s's just cancel out, and that gives me back the measurement, or right, the vector written in whole components. So this way of expressing r as x prime I prime plus y prime j prime is equivalent to expressing r in terms of the old coordinate systems xi plus yj. So in other words, we see that there are two ways in which things can scale. Any vector which scales in the same way as the basis vector or the unit vectors is called a covector, because it scales in a way, it scales together with the basis vectors. So covector scales or transforms in the same way as the basis vectors, or the unit vectors, as the basis unit vectors, basis or unit vectors. Conversely, vectors which transform in a way which is opposite or contradictory to the unit vectors are called contra-vectors. And an example of that is the position vector, which we typically use as the archetypical example of what a vector is. So it turns out that position vectors are actually contra-vectors because they scale or they transform in a way which is contradictory or opposite to that of how basis vectors transform. So vectors which transform, which transforms contra to basis vectors are called contra vectors. And an example of a contra vector is the position vector, just like the way we saw right now. So an interesting question now is, if you've looked at some of the modules that we have developed for functions of more than one variable, we introduced a derivative of a scalar function, which is called the gradient of a scalar function, which itself, we claim that the gradient itself is a vector. So can you now use this knowledge to figure out that if the change in a function of more than one variable is given as the gradient of that function dotted with, say, changes in the position vector, then what do you think, what kind of a vector do you think the gradient vector is? Is it a covector? Is it a covector? Or is it a contravector? So I leave that as a question for you. Do comment and do like and subscribe this channel if you find this content useful, but do comment and tell me what your answer is, and then we can continue with the discussion. Thanks for watching.